This is the validator we are going to test. The only thing that it checks is if we pass the correct redeemer, that should be any negative number or 0 after a deadline. For that, we created this custom datum type that is actually unnecessary because we could just pass this POSIX time, but I wanted to show how you can use both regular and custom types for your validator. And we also pass a redeemer of type integer. We pattern match custom datum to extract the actual deadline, name the redeemer R and the context CTX, and then we check the two conditions. One is that we expect that negative redeemer, and we check that just by comparing if the redeemer is less or equal than 0, that's it. And also we check if the deadline has been reached or not. For that, we do the same as previous lessons. We get the info from the context, and then we check if the deadline has been reached, meaning that if the valid range of the transaction is inside, it's contained in the time range from the datum up until infinity. So that's it. It's a pretty simple one. There's nothing more. We have just two functions that are the same as always. Wrap the validator and to actually compile the validator. So this is the validator we're going to test. Let's go to our testing suite. Here's our main entry point for the testing. Same as before, we have the default main, the testing group with a short description, and then a list of all the tests we want to perform. We have two values that could be combined in different ways. So we should have at least 4 tests for the different combinations of redeemer and deadline. But I also added the test for the 0, that is the limit between the correct and incorrect redeemer. So we have 6 tests. And as you can see, the explanation of the test tells the whole story. We have a test where the user 1 logs and the user 2 takes with a redeemer of value, in the first case, negative 42, because it's negative. The validator should be okay with that. And it's also after the deadline. So this one should succeed. The second test is the same after the deadline and the redeemer is 0, so it should also succeed. Third one is 42, so it should not, no matter the deadline, and so on and so forth. Actually, just the first two should succeed. Any other combination should fail. And how do we test it? Actually, it's the same test in all cases. The difference is the parameters we passed. In the first 3 cases, we provide a datum of 50. As you can see, 50 is of POSIX time. And then we have 3 different redeemers, negative, 0, and positive. This deadline of 50 should be okay because down here, we are hard coding when we are trying to consume the transaction. We're going to make user 1 create the different UTXOs with these datums, but we're going to always consume at the same time. In this case, after user 1 creates the transaction, we wait for 1,000 and then consume. So in the case of the first 3 tests, the deadline of 50 is smaller than when we actually consume it, so the deadline shouldn't be a problem. And the last 3, the deadline is a long time after we're trying to consume, so it should fail no matter the redeemer. Now let's see how we can create this test script. We start with a couple of helper functions, the hard-coded time that we have to wait before consuming the UTXO at the script. Then the function to set up as many users as we need. In this case, we only need 2 users. Then we import the actual validator from the on-chain module. In this case, if we go to the top, we see that the negative var time validator is imported as on-chain. So in this case, we are taking the actual validator and saving it here. And then we're going to create two helper transactions, one to consume and one to create the UTXO at the script address. Transactions are monoidal values. Lars explained in the previous lesson the concept of monoids. So you know that monoids have an operator to combine two values into one. In this case, we leverage this operator to combine a list of monoids using this mconcat value. As you can see, mconcat takes a list of monoidized values, in this case a string, a hello, an empty Haskell, and exclamation mark string, and applies this operator to combine all of them in a single value. This is really useful in this case because we can create a single complex transaction by combining multiple simple ones. In the case of the lock-in transaction, we create it by combining two. One that specifies everything the user has to spend to create the transaction, and one that indicates how we have to pay to the script. To create the transaction that the user has to spend, we have to pass this value of type user spend. This value contains all the UTXOs that have to be consumed for the user to be able to pay for the transaction. We have this value, this user spend value as a parameter because it depends on the state of the blockchain. So when we are actually making all the transactions, we are going to get the current value of this user spend and use that one and pass it to the lock-in transaction to actually spend the correct UTXOs. And then we create this transaction to pay to the script that takes the validator that we want to pay to. Then it takes the actual datum of the validator. As you can see, we are creating hash datum based on the custom datum we have on the on-chain code. So here we have the POSIX time that we provide, and this constructor provides the actual custom datum that we need for the validator. And finally, we provide the value that we want to lock. At the end of the day, this pay to script function returns a transaction. This user spend function returns also a transaction. And this mconcat function combines those two transactions in a single one to return a transaction. So this is how we build the lock-in transaction, and pretty much the same deal with the consuming transaction. The key difference is that because we have to consume a specific UTXO, we have to provide the reference and we have to provide the redeemer. As you can see here, instead of pay to script, we have the spend script function that also takes the validator, but in this case, it takes the reference of the UTXO we want to consume, it takes the redeemer, and then the actual custom datum again. And because we are consuming this UTXO, we have to pay someone the value that we are unlocking. So we combine this spend to script with pay to key that takes an user and a value, so we can indicate that we want to pay the unlocked value to this specific user. We combine these two transactions to get the actual consuming transaction. And that's it. Those are the two new transactions we have to create. And then, same as the previous video, we have to actually create the test by running several actions in our state monad. So we create the test script function. Let me center a bit. It's a bit too long, but it finishes there, so don't worry. We have this test script function that takes the datum in POSIX time and takes the redeemer in integer and runs the blockchain and returns nothing of value. The first thing we do is set up the users. We only need 2 users this case. Then user 1 logs 100 ADA in the validator. For that, we first create the actual value that we want to log. We pass this integer to the ADA value function to create a value of type value. Then we use the spend function that takes a pubkey hash and a value and returns all the UTXOs in that pubkey hash needed to pay for that value. This is the value of spend that we said we needed before. So we are ready to actually submit the login transaction. We pass the parameters needed, the datum, the spend transaction, and the value we want to pay to the login transaction, so we get a transaction back, and we make user 1, the one we are consuming the UTXOs from, submit the transaction. And that's it. Now our validator has a UTXO containing this value and logged with that specific redeemer. Then we wait for a bit and we start the process of consuming the script's UTXO. The first thing we need to do is to query all the UTXOs from the script address. Because we know there's only one UTXO, we pattern match to extract the reference and the actual output. We create a time interval based on the current time. In this case, we waited for 1,000 milliseconds, so this current time radius that we passed 100 as a parameter is going to create a time interval from 1,000 plus minus 100, so from 900 to 1100. This is our current time interval that we're going to use to submit the transaction. Now we have to actually create the transaction. We're going to use the consuming transaction we just saw. We are going to pass all the parameters needed. As you can see, we use TXOut value to get the value of the output we are trying to consume. And then once we have the transaction we were promised, we add this restriction that should validate in the time interval we specified, and we get our final transaction. Now we can submit the transaction. The one that submits the transaction is user 2, and all the changes we wanted to do are done. Now the only thing left to do is to check that everything is as we expected. We take all the values at user 1 and 2 addresses and check that the value 1 is 900 because user 1 gave 100 to the script. And we also check that user 2 has 1100 because it consumed 100 from the script. The script should be empty. And unless all this is okay, we log an error saying, hey, the final balances are incorrect. And that's it. There's nothing more. Now let's actually run the tests. Let's make this bigger. And we can say Cabal test week 6 and the name of the file. And there you go. All tests passed and we successfully unit tested our smart contract.